Hello and welcome to The Explainer. If you're focused on understanding exactly how the renewable energy industry measures its true physical footprint, well, you are definitely in the right place. Today, we're going to decode the SASB Sustainable Reporting Standards, specifically looking at wind turbine materials efficiency. We are taking those dense, complex regulatory texts and distilling them down into the precise engineering metrics that are literally defining the future of wind technology. Let's get into it. Okay, let's dive into this. Here's our roadmap for today. First, we'll look at wind tech sustainability standards. Then, why materials efficiency actually matters. From there, we'll get into tracking top consumed materials, calculating top head mass, and finally, optimizing future turbine design.
So, kicking things off with Section 1, Wind Tech Sustainability Standards.
To really grasp this, we first need to understand the broad regulatory framework that actually governs these engineering metrics. So, where do these rules come from? Well, the standards we're analyzing today are the SASB standards, specifically version 2023-12 for the renewable resources and alternative energy sector. Now, these standards are overseen by the International Sustainability Standards Board, or the ISSB, which operates under the IFRS Foundation. What this means for wind technology and project developers is that this isn't just some niche guideline, This is a comprehensive, globally recognized baseline for sustainability-related financial reporting. Under these SASB standards, companies in the wind tech sector are asked to report on 4 main disclosure topics. They have to cover workforce health and safety, ecological impacts of project development, materials sourcing, which deals with things like rare earth elements, and finally, materials efficiency. Now, while all of these are absolutely vital to a project's lifecycle, today we're zeroing in entirely on that last pillar. So, the crucial point here is that we are going to break down exactly how materials efficiency is measured and reported in the real world.
Moving right along to Section 2, Why Materials Efficiency Matters.
Before we hit you with the heavy calculations and the specific metric codes, we really have to ask ourselves, why focus so heavily on materials efficiency in wind tech? I mean, after all, wind is a renewable resource, right? So why are we so incredibly concerned with the physical materials used to capture it?
Well, the answer comes down to cost and scale. You see, the long-term success of the wind industry completely depends on producing energy at a lower cost than other sources. And to capture more wind, turbines are continuously growing in size. We're talking both in tower height and the massive swept area of the rotor. To put that into perspective, a single modern turbine tower can require hundreds of tons of steel. That is a massive amount of metal. And because inputs like steel have historically faced extreme price volatility, making highly efficient use of these materials is absolutely vital to keeping production costs down and scaling up operations sustainably.
All right, that brings us to Section 3, Tracking Top Consumed Materials.
Now that we understand the economic and physical stakes here, let's transition to the very first specific quantitative SASB metric we need to tackle today. This brings us to metric RRWT440B.1. The standard explicitly requires entities to disclose the weight in metric tons of the top 5 materials consumed in the greatest amounts in their delivered wind turbines. We are talking about tracking the absolute heaviest inputs here, which typically include materials like aluminum, carbon fiber, copper, fiberglass, and iron or steel. Now, what's really interesting about this is what we like to call the rule of exclusion. When a company calculates the weight of those top 5 materials, the standard is very strict about what actually counts. The reported weight must include the materials in the final delivered turbine, specifically the nacelle, the blades, and the tower. But, and this is a big but, it explicitly excludes the weight of materials consumed as manufacturing waste, as well as freight, storage, and critically, the installation foundation. So you're measuring the product itself, not the massive concrete slab it sits on or the scrap left over on the factory floor. So, let's see how this all builds into the reporting structure. You don't just report one massive, lumped-together number for the whole company. These consumed material weights actually have to be broken down according to specific wind turbine classes defined by the International Electrotechnical Commission, or IEC. Based on the turbine rating, companies categorize their data into Class 1 for high wind, all the way down to Class 4 for very low wind, plus a special Class S for extreme or custom wind conditions. This is super helpful because it allows investors to compare material efficiency apples to apples based on the specific aerodynamic demands of different turbine types.
Let's turn to Section 4, Calculating Top Head Mass.
Okay, so that covers the raw materials. Let's shift our focus to the second, highly specific engineering metric required by the SASB standards. This is metric RRWT440B2, the average top head mass per turbine capacity. And again, this is broken down by those IEC wind turbine classes we just talked about. I want you to think of this metric as the ultimate efficiency ratio. It measures a turbine's physical footprint against its actual power generation capabilities. Basically, how much heavy machinery do you literally have to put up in the air to get a megawatt of power?
To calculate this correctly, we have to carefully deconstruct the turbine anatomy. Step 1, you take the mass of the turbine nacelle, that's the housing way up at the top of the tower containing the generator and gearbox, and you combine it with the mass of the turbine rotor. Now, step 2 is incredibly important. Actually, it's a very common trap. You must entirely exclude the mass of the blades from this top head calculation. No blades. And finally, step 3. You divide that combined mass by the rated turbine capacity, which you might also hear called the nameplate capacity. That just represents the maximum generation output of the turbine.
And this brilliantly illustrates how simple the final math really is once you isolate the correct parts. You just take the mass of the top head in metric tons, again without the blades, and divide it by the rated capacity in megawatts. Your final reported metric is delivered in tons per megawatt, or TMW. It's that straightforward. And of course, the lower the number, the more efficient the design is at generating power relative to the sheer mass it requires.
Finally, we arrive at Section 5, optimizing future turbine design.
Now that we've mastered the hard quantitative math, let's transition from those rigid numbers to the final qualitative reporting requirement. SASB metric RRWT440B.3 requires companies to move beyond just listing their stats. They actually must describe their real-world design innovations. Companies have to explain exactly how they are optimizing materials efficiency. This could be physical design innovations to reduce turbine or tower weights without sacrificing structural strength. But, it also includes non-physical optimizations. We're talking about advancing operational control software, like SCADA systems, which handle supervisory control and data acquisition, to really improve that capacity factor. And naturally, they also need to detail their strategies for minimizing the waste created during manufacturing in the first place.
So we've seen how precise engineering calculations, from isolating the top head mass to tracking absolutely every ton of steel and fiberglass, translate into standardized financial data. Which leaves us with a critical thought to ponder. How will today's material efficiency dictate the global scaling of renewable energy tomorrow? Because the faster, lighter, and smarter we can build these machines, the quicker we can transition the global grid. Thank you so much for joining me on The Explainer to unpack these standards, and as always, keep learning.